Welcome to chapter 9. In this chapter, we're going to talk about ionic and covalent bonding. The first part of this chapter, the first video, I'm going to introduce ionic and covalent bonding and their properties. In the second part, we're going to focus on covalent bonding, and we will start drawing the molecules and the structures, and then the rest of the stuff that comes in this chapter. Okay, so let's start with the definition of a bond. What is a chemical bond? Basically, any strong attractive force between the atoms in a molecule is called a chemical bond. There are three types of bonding: ionic bonding, covalent bonding, and metallic bonding. We will focus on these two types of bonds, ionic and covalent, and of course we start with ionic bonding. You know a little bit of each from chapter 2 when we were working on the name and the structures, but here we will learn them in more details. So let's see what is the ionic bond. Ionic bond is electrostatic attraction between positive and negative ions. So imagine that sodium chloride is going to form. Sodium, as you know, metals lose electrons. So sodium loses one electron because it belongs to group 1. And by losing one electron, it will assume the electron configuration of its previous noble gas, which is neon. We all know it from the previous chapter. So sodium changes to sodium ion, which is a cation. On the other side, chlorine is ready to gain an electron and change to chloride, which is an anion. So we have the cation and anion ready. As soon as they form, they will stick to each other via an electrostatic attraction. So they touch each other and they will stick to each other via an electrostatic force, a very strong electrostatic force. So they will stay together. That's how an ionic bond formed. So first, metal should change to cation, non-metal should change to anion, and then these positive and negative charges will stick to each other via a very strong electrostatic force. If you want to know the Lewis electron dot symbol for the atoms and ions, first of all, what is electron dot symbol? In Lewis electron dot symbol, we will only show the valence electrons. Not all the electrons. Like, for example, for sodium, it has 11 electrons, but we don't show all of those 11 electrons. We only show one electron. Valence electrons equals to group number. So for sodium, which is in group 1, we show an electron as a dot. We have one valence electron, so we show it as, let me just write it here, one valence electron. So we just show it as a dot on one side of the symbol. There are 4 sides for each symbol, and we can put maximum 2 electrons on each. For oxide, oxygen has 6 electrons and oxide will have 8 electrons, right? But the number of valence electrons is the same as group number. So how many electrons do you put around oxide? It has gained 2 electrons, right? 6 valence electrons for oxygen, neutral oxygen. Then it gains 2 electrons, and the number of valence electrons will be 8. All right? Okay, so let's move towards knowing the strength of ionic bond. I said ionic bond is very strong, so let's see what are the factors that affect the strength of an ionic compound. According to this formula, you probably know it from physics. If it's familiar, you had it in physics. So the force between the two charged particles depends on a constant times the charges. Here we talk about ions, so ionic charges, divided by the distance between the charges. Here again, ions, so ionic charges divided by the distance between the ions. So if you want to compare this force between two ionic compounds, NaCl and MgO, let's use this formula to determine which one has a stronger electrostatic force. Sodium has a positive 1 charge, chlorine has a negative 1 charge, right? So Q1 is positive 1, Q2 is positive 1. Negative 1, for chlorine. Here for magnesium, positive 2 and negative 2, you already know these from chapter 2. Q1 is positive 2 and Q2 is negative 2. So, which one has more or higher ionic charges? Magnesium oxide, right? And you learned from radii, the radius of sodium is more than the radius of magnesium, and radius of chlorine is more than radius of oxygen. So R in magnesium oxide is smaller than in NaCl. This is another evidence that MgO will have a higher force. F of MgO is higher than F of NaCl. This appears in the melting points. Melting point for NaCl is less than that of MgO. For example, if melting point of NaCl is 800 degrees Celsius, the melting point for MgO is 2800. So this strength between the ions appears in the melting points. Don't forget these two factors and this formula. Another thing we need to know is the ionic radius. We say cation loses electron, right? Is the let's say neutral atom that has lost electron. So like sodium loses electron to change to sodium ion. Keep in mind that radius of cations, positive charges, is always smaller than their neutral atom. And for anions, because they gain electron, the radius of an anion is always larger than the radius of a neutral atom. Why positive charges, or let's say cations, have a smaller radius? Because the number of electrons decrease, so effect of nucleus on the rest of the electrons increases. Nucleus has a positive charge, electrons have negative charge, right? When an atom loses electrons, the effect of nucleus will become more, because you say positive means the number of protons becomes more than electrons. Then the nucleus pulls the electrons more strongly towards itself, so the atom shrinks. Why anion has a larger radius? Because by increasing the number of electrons, first of all, you are putting electrons maybe on more layers, and also these electrons will have repulsion, right? And by increasing the number of electrons, nucleus won't have that much effect on the electrons. So all of these factors together, they cause the anion radius to be larger than a neutral atom. Okay, let's move towards covalent bond. We are done with the concept of ionic bonding, how it forms, the strength of ionic compounds. The rest of the focus of this chapter is on covalent bonding. You remember from chapter 2 that covalent bond is a bond which is formed by sharing a pair of electrons, not one single electron, one pair of electrons, at least one pair of electrons between the two nonmetals. So let's say these are two random atoms, whatever you want to imagine. The electrons will be shared in this region. So the two atoms, we call it overlap. This is the overlap area. Overlap means they cover each other. The atoms start getting closer to each other. The energy decreases until they cover each other and they will form a place for shared electrons. The distance between the two centers, the distance between the two centers of the atoms is called bond length. They go inside each other, right? So this bond length is less than addition of the two radii to each other. So the distance between the two centers of the atoms in a covalent bond is called the bond length. As soon as the bond is formed, the energy becomes minimum, because for each bond, some energy is released. You will learn about bond energy at the end of this chapter in the next video. Alright, so now you know about the covalent bond. Do you remember this concept, electronegativity, from previous chapters? We said it's a tendency of atoms to attract shared electrons in a covalent bond. We said atoms share the electrons, right? So sometimes some of the atoms want to pull the shared electrons more strongly towards themselves. It's like a rope pulling contest. Sometimes one side pulls the electrons more strongly towards itself. The only thing we need to know is the trend of electronegativity, so we can talk about the rest of the concepts that I'm going to introduce. We said, if you remember, we said electronegativity increases from left to right across a period and from bottom to top in a group. So the electronegativity of fluorine, if you can imagine, fluorine is on farther right and top. So the electronegativity of fluorine is the highest, is 4. You don't have to memorize any electronegativity values you will be given. I just want you to know, based on this trend, we expect fluorine to have the highest electronegativity, which is the same. And for francium, on the bottom of group 1, you expect the lowest, which is correct, which is 0.7 only. So, let's see how we can use this electronegativity concept in our covalent bonds. Look at this carbon-chlorine bond. According to the trend that I introduced here, which one is more electronegative? Carbon or chlorine? Check with your periodic table. I'm sure you will say chlorine is more electronegative. So, on the more electronegative atom, seems like there is more density of electrons. If you look at this molecule under microscope, you will see such a density of electrons more towards chlorine, which is more electronegative. So we put a partially positive, we call it partially positive. It's a delta notation. It's a Greek alphabet letter, the small delta. The capital delta was this, right? The small delta is this. So we put a delta notation on, this is negative. On chlorine, we call it partially negative. So it's partially negative. And on top of carbon, we put partially positive. We say partially because comparing to chlorine, carbon is more positive. Comparing to carbon, chlorine is more negative. This is something relative, something partial, not absolute. So, if there is an electronegativity difference between the atoms that participate in a covalent bond, such a bond is called a polar covalent bond. It's polarized. One side is more negative, one side is more positive. So we call it a polar covalent bond, or just basically we call it polar bond. There is a measure, there's a criteria for determining the type of bond based on the electronegativity difference. We say if the electronegativity difference between the atoms involved in a bond is less than 0.5, the bond is called nonpolar. Like between the two identical atoms, for example, chlorine, chlorine. What do you expect to be the electronegativity difference? 0, right? If this electronegativity difference is between 0.5 and 2, it's called a polar covalent bond or just polar bond, like what we saw for carbon and chlorine. And finally, if this electronegativity value is equal or more than 2, the bond is not covalent anymore, means the atoms cannot share the electrons. We said it's the rope pulling contest, right? This is nonpolar, this is polar, and then finally they separate from each other if electronegativity difference is too high. So instead of covalent bond, then we will have ionic bond like NaCl. So now your question might be, how do I know how to get these differences and find out how to determine the type of the bond? I brought an example here for you. Let's work on it. First of all, these values will be given. So you are expected to work with these. Determine polarity of each bond. Bond between carbon and hydrogen. Polarity of each bond depends on electronegativity difference. So let's find the difference between the electronegativities. For carbon is 2.5. Let me change my marker. 2.5 minus hydrogen 2.1. It's just how much the difference? Tell me. 0.4. So according to this trend, is less than 0.5. It's a nonpolar bond. I call it a nonpolar bond. Repeat the same thing for NaF and for OH. So for NaF, the electronegativity of fluorine is 4 minus 0.9. Always use this the larger because we want to have a positive value, okay? So it would be 3.1, huh? It's more than 2, and as we expect, because this is a bond between a metal and non-metal, so we call it an ionic bond. It's not covalent anymore. And finally, let's find the difference between O and H. Oxygen 3.5 minus 2.1 is 1.4. Under which category we put it? Between 0.5 and 2, which shows a polar bond. Okay, I hope you learned about both ionic and covalent. In the next video, I'm going to work on the loose structure of the compounds, and then we will talk about the rest of the stuff as far as resonance structures, formal charges, and at the end, we finish this chapter with bond energies. Don't forget to practice.